Hi guys, so today we will be trying to today we will be trying to solve this problem from CMI 2025 question number 8, right? Uh, so it is saying to pick the correct statements from below. Our first option is if fz is function, so let me just write it, right? So f is defined from C to C, and f satisfies CR equation Cauchy-Riemann equations at z equals to 0. This is given. Then fz is complex differentiable at z equals to 0. And this is not always true, right? Because, right, satisfying a Cauchy-Riemann equation at a particular point doesn't necessarily like guarantee us that this is complex differentiable, right? For that, I mean, okay, so let me just write, let's say f is u plus iv. For that, we also need ux, Vx, Uy, and Vy to be continuous, like near neighborhood of that point zero. So this always might not happen, right? We can find a counter example. So this is not always true. So this is false. I mean, we can generate an example. So now for our option B, it is saying that the function. So let me just write down the function. Uh, so let me just say. Let me just write down the function. Okay, is holomorphic, and also it is saying that this is holomorphic. This is holomorphic on all z belongs to C, such that zero greater less than mod z less than one. So basically, yeah, this punctured disk, right? So we have this open disk. So we have this, and yeah, we have a puncture here or a hole. So it's punctured at zero. So yeah. So he's saying the function this is holomorphic on this and has a removable singularity at z equals to 0. I mean, I mean, like apart from 0, all the points, like apart from 0, if we, like if we take account for all the points, this is like this will be analytic, right? Yeah, only 0 is the problem here in the denominator. So it's holomorphic on the rest of the right punctured disk, and now it is asking for if it has a removable singularity z equals to 0. So we just need to find limit z tends to 0 fz. If it exists, then yeah, it will have removable singularity, and using our yeah using our like Riemann's removable singularity theorem, we can extend it to a holomorphic function in that whole disk, right? Uh, yeah. So basically, all we have to do is check for the limit. uh, Limit z tends to 0 f of z. This will be okay. So we just need to find this limit now by mod z to the power 6. Now, like you notice that mod z to the power 6 is given, and we know mod z square, right? Mod of z to the power mod z square is nothing but z times z bar. Okay, so since it's mod z square, like power of L to the power 3, I mean cube. So this will turn out to be, right, limit z tends to 0 sine z minus z cube, right? Okay, let me just, yeah, so this will turn out to be this, mm, by divided by um, z, um, yeah, z cube times z bar whole cube, right? So this will turn out to be like this. So like since z tends to 0, we can actually do this, and so basically our limit will be limit z tends to 0. Uh, okay, so actually I was wondering that, like, okay, this I mean I like I actually typed it out in LaTeX, LaTeX, right? So I think I made a mistake, a typo. This would be z bar cube, right? So this will be z bar cube. Okay, so I made a pretty big mistake here. So this will be z bar cube, and so this won't get cut. This and this will get cut. So sorry, there was a typo. Like you can check the official paper. So yeah, so this will be sine z minus z by z cube. Okay, and and we can, like, see that, like, for sine z, if we'll have a Taylor expansion of z minus z cube by 3 factorial plus z to the power 5 by 5 factorial minus z to the power 7 by 7 factorial, and so on. Like, we only need the power and this term, second term, I mean first and second terms, because the rest, I mean, they will tend to zero because it has higher powers, right? So they will get cut, and yeah, since denominator is smaller, degree, so they will tend to zero if we take the limit. So we are just ignoring them. So this will be limit z tends to zero. Mm, so this will be, uh, yeah, so basically, right, after taking the limit, we don't actually, we see that this is minus 1 by 6. And this will come out to be minus 1 by 6. Right. So this will come out to be minus 1 by 6. Right, because z and z will get, like, cut, and minus z cube by 3 factorial, since z tends to 0, we can just, yeah, so this will come out. So limit will exist, and so we can clearly say that will be, this will be true. Now, for, I mean, so let us look at this option C. There exists a holomorphic function on this mod z greater than 3 whose derivative is this z by z minus 2 whole square. Okay, and option D is the same kind of option. It is saying that there exists a holomorphic function on the upper half plane. Z belongs to C. They've defined the set. Z belongs to C such that, I don't know, tau z. I think this will, okay, this will represent the imaginary part of z. So imaginary part is 0. So it's essentially, so let's say we have this. So basically all this, right? I mean, this will not include this, like the x-axis, because imaginary part is not 0, it's greater than 0. So it is saying that, does there exist a holomorphic, I mean, there exists a holomorphic function on this upper half plane, okay, on this upper half plane, whose derivative is this. Okay, so now if we look at it carefully, you will see that z by z minus 2 whole square, like, it's similar to the first option, but it's like z square plus 4. So we can write it as z minus 2i into z plus 2i. And you'll notice one thing that, okay, uh, 2 is right here, right? I mean, 2 comma 0, of course, obviously. So this is right here, minus 2i is here, and 2i is here. So yeah, this has a pole at, z equals to 2i, right? And 2i belongs to this upper half plane. But, and we know that if, in complex analysis, if there is a holomorphic function defined in a domain, I mean, it will be like, it will belong to C infinity, right? In that domain, basically it will be infinite times differentiable. But in this case, like, his first, I mean, the first derivative is this. Okay, this is not even continuous because it has a polar z equals to 2i. Right. So yeah, so how can such function exist whose derivative is this? Right. So yeah, so this statement is false. So this statement is clearly false. Now what about C? Now they're saying that there exists a holomorphic function on, okay, remember this function, this is the same function. Okay, z by z minus 2 whole square. There is a holomorphic function on this whose derivative on mod z greater than 3 whose derivative is this. Okay, so let me try to do option C. Okay, so let's just write gz is given z by z minus 2 whole square. And right, if I look at it carefully, so this is 3. So this, I mean, all the rest of the space. So there exists a holomorphic function of this whose derivative. So it is asking for an, so does this function, so does gz, does does gz has a primitive, right, or a anti-derivative, whatever, anti-derivative. like in this like region in mod z greater than 3. So now this z minus 2 doesn't have the problem that we had right use in option D, right? Because 2 is within this, so and we can clearly see this will be infinite times differentiable. Okay, so there is a chance. But one more thing that we should know, that one thing that should recall is that suppose that we have a function, let's say g here from the particular domain to C, so it's continuous in D, then I mean or holomorphic, then G has an antiderivative in D, like if and only if, right? Um, if and only if, right, these are all equivalent statements. Is gamma gz, this will have an antiderivative, right? And since G is holomorphic in this, so equals to 0, all right, along every closed contour, along every closed uh, contour in the domain, right? So in the domain, so let's say we have this is, let's say this is gamma, so integral gz dz needs to be 0. So does it follow that this is 0? I mean no, right? Because we can clearly see if we take gamma to be a circle, right, of a slightly bigger radius than 3, we can say 3.4, 3.5, or whatever. Let's just say take 4. Okay, let's just say this is 4, and let's just say gamma t to be e to the power, sorry, 4 e to the power it, such that as usual we just take we don't need any winding number, we just take one simple yeah, rotation of the of like, yeah, it goes from here to here. Okay, so okay, right. Now basically we can check that. So then integral gamma z by z minus 2 whole square dz. As you can see, so 2 is in mod z less than 4. I mean, yeah. So 2 is here somewhere. So 2 is here. So you be using the Cauchy integral formula. So we can see. So this will be uh, if we consider this to be f of z, so this will be f dash 2 by, sorry, into 2 pi I by 1 factorial, right? So what is fz? Fz is z, f dash z is 1, so this will be 2 pi I. So that is not equals to 0, right? So this doesn't follow this. Okay. So this option will not be true, right? So this won't have a like global like antiderivative or a primitive, right? Uh, yeah. And why do you need to check off this? Because this is not simply connected, right? I mean, GZ is already holomorphic. If the whole domain was simply connected, then we could have using Cauchy's like theorem, we would have easily said, well, okay, that integral along every closed curve will be 0, right? But this is not simply connected, right? Mod Z, this this domain is not simply connected, because if we take any point like here, we can't shrink it like without this overlapping with this hollow region or this hole, right? Okay, so yeah, so this will also be false, so only option B will be true. This was such a nice question, especially option C, right?